Distillation allows you to create smaller and faster models from larger and more powerful models. The technique is used to create faster, cheaper models for image diffusion, speech transcription, and possibly even to make GPT-4o Mini from GPT-4o. Distillation is powerful because, compared to training a model from scratch, it requires only about 2% of the data and 2% of the compute. In this video, I'll describe the entire distillation process, including model pruning, distillation and instruction fine-tuning. I'll then give a full code walkthrough for distilling a 99 million parameter model. By the end of the video, you should understand how to distill your own transformer models. I'll start by talking about a few famous models that are distilled, so you'll get a sense for how widespread this is. Then I'll go through a high-level description of how the process works, which means initiating a student model, which is the smaller model we want to train, then training it using distillation as opposed to doing full pre-training, and last of all, some instruction fine-tuning, which is actually pretty much the same as you would do if you were training from scratch. Then I'll go through step by step how I distilled a 99 million parameter model. I'm distilling it from a larger model, a slightly larger model, SmolLM 135 million parameter model. I'll show you all the process steps here through the pruning through the distillation, and then the instruction fine-tuning. And then I'll finish off with a few tips. Now, this video will show you an example for large language models, but the same approach applies if you're going to train, say, a speech-to-text model, or if you're going to train a diffusion model. You just need to make sure you're able to load the models and do the fine-tuning as I've shown, which, to be fair, is probably not completely trivial. So it'll be easiest to do a language model after seeing this video, although I'll show you some examples right up top of how this works for other types of model too. Okay, so the three examples I want to give are Minitron from Nvidia, which is a language model distillation, Black Forest Flux, which is a diffusion model distillation, and then Distil-Whisper, which is a text or speech-to-text model distillation. Now, in the intro, I talked about GPT-4o and potentially the mini model being a distilled version of 4o. I don't know if that's true, but it's one way they could do it. Broadly speaking, I would say there are two ways you can look at creating a family of models. One is the llama type approach, where you will take the same data set and then train from scratch models of different size, like 8 billion, 70 billion, and 405 billion. And the other approach you can take is you just train the largest model, and then you use that large model and distill the model down into a smaller model. And that will generally result in a more powerful, smaller model. Now, in practice, probably before training a massive model, you're going to train the smaller one as an ablation just to see how performance is going. So you probably have that smaller one anyway. But even still, it can be worth distilling the smaller model at the end from the larger one, because distilled models tend to be more powerful than what you can train from scratch. So the three examples I'll go through here very quickly will be Minitron. Minitron is an approach for distilling large language models, namely Llama 8B and also Mistral Nemo. Now, there's a paper here, a tech report on Minitron, and I just want to show you the performance comparison. So here we have Mistral Nemo, the base model, and we have some of the results. Let me see if I can increase my screen a little bit. And you can see, just for example, the Winner Grande evaluation is scoring 82.7. And this 12 billion model is distilled down into an 8 billion version. So that's a 1/3 reduction in size. And it's scoring 80.4. And you can go down and look through the other results. But basically speaking, you're getting a small deterioration in performance, but you're getting a faster model. Significant reduction in size. So we'll come back to this paper because it describes pruning in detail, which we'll talk about a little later. But this is the one example of how you can distill a language model. Now, another example is Black Forest Labs. They are a company that produces diffusion models for creating images. So you give some text, like the thumbnail I made for this video, and you create an image. And they, in the background, have trained some large Black Forest Flux model that is not released. It's a private gated model, but they have released distilled versions. They have two distilled versions they've released. One is the dev model and one is the Schnell model. And they're distilled in slightly different ways. This one is guidance distilled. This is time distilled. I won't get into the detail of that. You can maybe take a look at the Flux video I made earlier. But broadly speaking, they're releasing these distilled models that would have been a lot cheaper to make, but only sacrifice quality versus the big one probably by a relatively small amount. The third example I'll give is Distil-Whisper. Distil-Whisper is a distilled version of Whisper, which allows you to transcribe speech to text. It's actually developed by OpenAI. But if you go to Hugging Face and you go to Distill, you can find Distill Large v3. Now, the Whisper models come in various sizes. There's, I think, tiny, base, small, medium, large. And the Distill Large is a distilled version of large that is actually the size. I think it's more representative of maybe the small or medium, depending on how you think about performance. In fact, we can just look at some of the results here. So here we have the original tiny, base, small, medium, large. And then we have a distilled version, distill medium and distill large. So if we look at distill large here on the long form results, it's got a word error rate of 11.6%, which is actually only a tiny bit behind the word error rate of the original large model. But the relative latency is 5.8 times lower. So you have a nearly 6 times speed up in this distilled model, and only you're sacrificing error rate by a tiny bit. Now, this is on long form transcription. On short form, it's not quite as good. So it's scoring 10.1, which is a lower error rate. So it's an error rate between the small and medium model. So if you compare to, say, the small model, you're getting about a 2x speed up for about the same amount of quality. So you can see this is quite widely applicable. You can do distillation for an LLM, or it could be a vision and language model too. You can do it for diffusion, and you can also do it for transcription. And you can do it for any neural network. So what I'll get into now is the overall process for doing distillation, and I'll talk through each of the steps. The first step is you need to set up your student model in the small form. The next step is you need to distill the knowledge down into that student model. And then you kind of need to polish it off by doing instruction fine-tuning, which is pretty much what you would do anyway in a from scratch training. When we think about initialization, this is really just a fancier way of starting off of initiating the model compared to from scratch training. In from scratch training, you're going to initiate all of the matrices in a model as random numbers, or maybe you might have some policies like using identity matrices kind of with a diagonal, or maybe you might try and initialize them to be Gaussian, and there are various techniques that work a bit better than others. But broadly speaking, when we talk about training from scratch, the initialization is pretty much from scratch. And the idea with pruning here is that you can do a lot better than starting from scratch by basically robbing some of the weights from a larger model. Now, of course, you can't really rob all of the weights, because then you would have a model of the same size. So you have to decide which weights, which matrices do you want to copy and start off with. And broadly speaking, there are two ways to think about how you might rob weights from a larger model to get started. The first is layer-based pruning, and the second is width-based pruning. So layer-based pruning to get started, let's just look at a transformer model where we have, it's a language model going from the quick brown and predicting the next token. And we start off with an embedding layer, which converts the tokens into vectors. And then in every layer of the language model, which consists of attention and multi-layer perceptrons, in every layer, we transform these vectors until they get to the output, and we have a probability distribution that will tell us what the most likely next token is. So in this model here, I have two layers, each consisting of attention matrices and multi-layer perceptron matrices. And the idea of layer pruning is simply to remove some layers. So broadly speaking, if I remove 50% of the layers, if you set aside that there's some weights in the embeddings, then you're going to reduce the model size roughly by half. So the idea of layer pruning is just take out some of the layers, just like this. And it turns out that the best layers to take out are usually the final layers, except for the very last layer. This is shown very nicely in the Minitron paper. Sorry, this is the Whisper paper. Here's Minitron. And they have a graph just a little down here where they show a variety of options for layers to be pruned out. So here we've got a layer number on the x-axis. There are 32 layers. And they look at a baseline validation loss. So this is just perplexity. You want this to be lower. So in the unpruned case, the model is scoring about 2. Then in the orange case, they just drop 1 layer. Then in red, they drop, in red, they drop 8 layers. And in purple, they drop 16 layers, which is half of the layers. And so you can see when you go from dropping 1 layer in orange up to 8 layers in red, up to 16 layers in purple, the perplexity is going up. So this makes sense. The more layers you drop out, so the smaller a student you're trying to initiate, the worse the perplexity. But if you look within that purple curve here, you can see that the perplexity is lowest when we have dropped out 16 layers towards the end. So basically, perplexity is going to be lowest if we take all of the layers except for that last layer. And the reason I say except for the last layer is because you can see the perplexity goes up for all of these curves if you include removing the last layer. So basically, you want to step back a little bit from the final few layers and remove layers here within this kind of flatter portion. So in order to do a reduction from 135 million parameters down to 99, I'm basically going to remove roughly a quarter of the layers, and I'm going to remove them from this later part of the transformer, but I'm going to leave in the last layer. And maybe, I should have left in the last 1 or 2 or 3 layers, but roughly speaking, you want to remove them from the last layers here. So that's how layer pruning works. You're simply pulling out a few layers. And yes, the model will kind of output nonsense, but it's way better nonsense than random weights. And with just a little bit more training, you're able to get the model back to a point where it can produce useful content. That's the motivation why it's better to start by robbing weights instead of just initializing random. Now, the other approach is with pruning. So if we take this same transformer, and now if we zoom in on one matrix, let's just pick the K projection. So this is the matrix that's used to calculate the keys vector for a given input. But you can think of any or all of the matrices. Here I've got a square matrix that's 4 by 4. And what I would do with pruning is just decide to cut off one of the columns. Here I've cut off the last column. You could also cut off one of the rows. Now, when you cut matrices, you need to make sure that the internal dimensions and multiplications are all consistent. So you can't just arbitrarily cut the size of matrices, but you could consistently cut all of a multi-layer perceptron layer and then make sure it's compatible with the neighboring layers in terms of sizing. So yeah, this is naive width pruning where you just toss out some random weights. And this is another way to prune. Now, there's a better way to prune. In the same way we optimized which layer we should remove and found the last ones are the best to remove, you can selectively decide which weights in the matrices to remove. And you can do this by looking at activations. So what I mean is, if you take a matrix out of this first layer here, you can examine the activations, which are the outputs that come from this layer, and you compare those values, compare the values that the model predicts in a forward pass with the values that you get based on a test set of data. And by looking at this error, you can decide to remove weights that minimize the error caused in the activations here. So this is activation-based pruning. And this, it turns out, it's going to be a lot better than just randomly chunking off a column. But that being said, it's a lot more work because you have to figure out a data pipeline and an algorithm that is going to either iteratively or in some other way decide which weights you want to pull out. Now, going back to Minitron here, there is a comparison between the width pruning and the depth pruning. So let's see if we can find that. I think it's back up in the table I had. And indeed, here, if we prune LAM at 3.1, so now they're training a model based of LAM at 3.1 8B, not NEMO anymore. And they're pruning it basically from 8B down to 4B, so they're cutting the size in 2. And you can see the perplexity here by comparing the depth pruning, which is the layer pruning, and the width pruning. You can see that the scores, which we want to be higher, are higher here. They're bolded for the width pruning. So based on this paper here, it looks like you're better off doing width pruning, with the caveat that it's not naive width pruning. It's got to be activation optimized or some other algorithm to pick the right matrices to cut down on and where to cut down on them. So my conclusion for pruning here is, if you want to do something straightforward, it's probably easier to do layer pruning. and just remove some of the later layers. If you want to do something more fancy, then you can look at width pruning and adding an algorithm to decide on how to do the width pruning. So that wraps up pruning, which, as I said, is basically a shortcut in training whereby you initialize your model to a point that's a lot closer to the final state you want it to be in than just randomly initializing the model. Once you've got the initialized model, the next part you come to is the pre-training. And the classic technique here would be to do pre-training with a large data set. The only difference would be that we're starting from a better starting point. So even if you do pruning and you do classic pre-training, it's possible you're going to have a shorter training or at least better results than just initializing with random weights. So we've already introduced one improvement, but the next improvement we introduce is distillation. And this means rather than only relying on the data to update the weights, we're going to rely on what a teacher model or a larger model would predict for the next token. If we compare this in table format, we look at classic pre-training and distillation. The relative amount of data you need for pre-training is, let's say that's 100%. Well, for distillation, you probably only need 2%. Now, maybe I should put that in a bigger range, but the amount of data you need is far less than what you need for pre-training. And that roughly is going to be true for compute as well. You're only going to have to do 2 to 5% the number of forward passes because you're using a lot less data. Now, you will have to forward pass on both the teacher and the student, but the student is a lot smaller than the teacher. So as a percentage of the compute that you used for the teacher, you're still going to be down around 2 to 5% for distillation. The way we think about making updates to the model or the back propagation is going to be different for pre-training and distillation. For pre-training, we always compare the model's prediction to the next token in the data. So if I say the quick brown fox and I predict the next token, I'm going to compare the actual value, which is jumped, with whatever my model predicted. Whereas in distillation, I'm not actually going to look at the actual value of jumped. I'm going to instead look at all of the probabilities the teacher predicted. And the teacher might have predicted 50% for jumped and 30% for leaped and 10% for rolled. So we're going to compare over a distribution of the teacher's predictions, not just one actual prediction. And mathematically, the way we do that is using cross-entropy in the pre-training case, whereas we use what's called KL-divergence in the distillation case. Now, I'll describe these hopefully in simple terms. Just a quick note, you can in principle add pre-training. So you can add the cross-entropy loss to the KL-divergence loss and kind of do a hybrid type of distillation. It seems like the consensus is that you should just do pure distillation and that performs better than adding in even some cross-entropy. Although that's just based on a sample of a few papers I've looked at. The intuition I have is if you are looking only at data, you will always see some spikes in the data. Whereas if you're only looking at the teacher is already essentially a smoothed version of the data. And so you tend to have fewer spikes and you tend to have a more information dense process if you're distilling with the teacher because it provides a full distribution of probabilities, not just a single next token. To understand cross-entropy versus KL-divergence, it's easiest to think of an example. So let's think of a language model and predicting the next word here. My favorite animal is the, and we want to just predict this word. So this is a special language model that only predicts the next word in the sentence, and it only has a vocabulary of 3 words: dog, cat, and bat. So obviously I'm oversimplifying greatly, but let's think of what this looks like with cross-entropy and KL-divergence. So in the cross-entropy case, we know the next word, which I'm going to say is dog. So the next word for the purpose of back propagation, the actual probability is 100% going to be dog and 0% cat and bat. And when we forward pass, the student in its current stage is predicting dog at about 60, cat at about 25, and bat at around 15. And so the way we will penalize the model and update the weights is actually based on the difference here in the score that the model assigns to dog. And we'll see that in the equation in a second. But in the cross-entropy loss approach, we're comparing this single actual next token with the model's prediction for that token. By contrast, in the KL-divergence approach, we're not comparing at all with the actual next token. We're comparing with what the teacher thinks the next token is, which is in gray. And the teacher thinks that dog is 50%, cat is 30%, and bat is 20% here. And actually, we will update the model not just on dog, but based on all of the differences in predictions here. So we'll incorporate the difference between student and teacher in dog, cat, and bat. And we'll actually weight these according to the probability of the teacher's prediction. So we're going to put 50% weight on the difference between dog, 30% weight on the difference, actually the log difference of cat, and then 20% weight on the log difference of the student and teacher model for bat. And you can see that in this probability here. So the KL-divergence or Kullback-Leibler is going to be the probability of the teacher multiplied by the log of the ratio of the probabilities for each of these three cases here. Whereas in cross-entropy, we've got y, which is the actual distribution, times log of y hat, which is the student predictions. And because the actual token is always going to be a 1 for whatever the next token is and zeros for everything else, this cross-entropy simplifies down to just 1 times log of the student's prediction on whatever the next actual token is. So yeah, to re-say that one last time, in cross-entropy loss, we're effectively only looking here at the most likely token and the probability, log of the probability the student has. Whereas in the KL-divergence case, we're looking at the whole distribution and we're weighting the differences according to the teacher's prediction. So that's the difference. Just one technical comment. This is called forward KL-divergence. It's also possible to weight the differences here according to the student's prediction instead of weighting it according to the teacher's prediction, and that's called reverse KL-divergence. In theory, if you are doing forward divergence, if you're doing reverse divergence, you're more likely to match the mode or the most frequent prediction within a data set. So that's the theoretical difference. There are papers that have looked at doing forward versus reverse, and there are arguments maybe for reverse being a bit better, but I think you really have to try it in practice, and I don't know categorically whether forward or reverse would be better, but we're going to use forward divergence because it's more commonly used. And that brings us to the third step of distillation, which is not going to be very new if you've watched some of my videos before. It's the instruction fine-tuning set. This is where we get chat type data and we just do some straightforward fine-tuning on the student rather. There's no involvement of the teacher at this stage. We're just doing supervised fine-tuning, and potentially you could do some preference optimization, either DPO or PPO, or maybe you could do both of these at once if you want to look at ORPO, which is odds ratio preference optimization. And you can check out my video on that if you want to dive deeper. For today, I'm just going to do some supervised fine tuning. So I'll keep it fairly straightforward. So to put everything together, and this is going to be my approach for distilling the 99 million parameter model. I'm going to start with a teacher model of 135 million parameters. It's the SmolLM model developed by Hugging Face. Then I'm going to initiate a student model by layer pruning. So I'm going to prune off some of the last layers of the 135M model to get 99. Now, just to clarify, I'm using the base models here. I'm not using the instruction model. The reason for that is because I'm going to use pre-training data, which is not instruct formatted. And I'm going to distill on 2% of that data. So I'm taking the SmolLM corpus, which is publicly available. It's basically a mix of Cosmopedia and FineWeb. You can check out my video on FineWeb if you want to understand how that data, it's a high quality data set. It's a filtered version of, heavily filtered version of Common Crawl, including filtered using language models. And then lastly, I'm going to do supervised fine tuning on Web Instruct. Actually, Hugging Face, in developing SmolLM, they do supervised fine tuning on a few other data sets as well, which, yeah, is probably important for performance. So I'm not training enough here to get the best performance. I'm more giving you the steps and code of how you would want to do it. So with that, we'll move on to the distillation code walkthrough, and I'll show you the pruning, the distillation, and the instruction fine-tuning. And for the scripts, I'll be working out of the advanced fine-tuning repository. you can get lifetime access to it over at trellis.com/advanced fine-tuning. And within the repo, I think we're coming up on 348 members of the repo now, a little bit more than some of the other repos for vision, transcription, and inference. So I've cloned this repo locally, and what I want to do is check out the distillation branch. So I'm going to go down here to distillation. Of course, there are many other branches, including branches for ORPO, for supervised fine-tuning. You can take a look over at trellis.com. But for the purpose of distillation, you'll find there are a few files here that I'm going to go through in detail. And I will try and describe everything at a high enough level and put some free resources in the description. So if you're not in a position to purchase, you can at least work by yourself to achieve the same effects of what I'll show today. So there are a few key scripts here. The first one I'm going to look at is the pruning script. So layer pruning v10. That's going to allow me to prune the model and create the student. I'll push that up to hub. Then I'll run the distillation script. Now that's a Python script. I'm not going to run it from a notebook. I'm going to run it from command line because I'm going to use a large number of GPUs. And I'm going to set the parameters for that in config v10. And then last of all, I'm going to look at the instruction fine-tuning, which is the supervised fine-tuning to improve the performance of the model. That script also has the ability to run inference, and we can run some test questions on the model right there. So the first step is this layer pruning script. And what I'm going to do to run that is head over to RunPod. And I'm actually going to find in the one-click LLMs repo, this is a public repo, I'm going to find my fine-tuning template. Click on that and start up a pod. Just for doing the layer pruning, especially because it's a small model, I only need this cheapest instance, A40 with 48 gigabytes of VRAM using the fine-tuning notebook setup. And I'm just going to run this in Jupyter Notebook. So in Jupyter Lab, and I'm just going to run this in Jupyter Lab. I'll upload a notebook from my local instance. So the Jupyter Notebook is up and running. And I'm going to upload here the layer pruning script. And actually, I'll upload the instruction fine-tuning script as well. And optionally, you could use upload this upload folder script. It can be useful for uploading models later on. And I'll go into this layer pruning notebook and run my installations. The next thing to do is to inspect the model, just so you can see how many layers there are. The model that I want to prune is SmolLM, not the Instruct version, the base version. So I'm going to run this cell here, and that's going to print out a description of the model. Let me increase my screen size. And this is nice because it shows me I've got 30 layers. So I'm going to be pruning from those layers. And if I was doing width pruning, I would be pruning the width of some of the matrices here. So I can run that model. And next, I'm going to look at some scripts for pruning. So I have a few scripts. One is for layer pruning only. One is for pruning every second layer, but not the first or last. I did run this and it didn't seem to be any better than pruning the last layers. So I'm not going to look into too much detail. And the last one here is naive width pruning. So I'll quickly show that, but this is not optimized. It doesn't minimize the activation losses. So I just give you that caveat that this is kind of a naive way to do layer pruning. By the way, it allows you to prune both for width and for layers. So in the layer pruning, very, very quickly, the approach here is to load up the model, then count the parameters and print how many parameters there are, figure out how many model layers there are by printing the length. And then I'm going to decide how many layers I want to keep. And the decision on how many to keep is determined by the target parameters divided by the original parameters. So when I run this code, I'm going to set the target parameters to, I'm actually going to set it to 90,000. And it's going to round up to whole layers. So that's kind of what ends up giving me 99 million parameters. So I have my layers, I have my total layers, I have my layers to keep, I have my layers to remove, which is just total minus layers to keep. And then, I'm going to make sure that I select the layers in a way that excludes the last layer. So that's why I have here the -1. Then I'm going to, basically set the layers of the new model, the student model, to be the selected layers. So this is the key step here where I'm setting the model to be the subset of layers that I've selected. And once I've got that model, I can return it, and that's pretty much the pruning. So you can see I pass in the Hugging Face model, I pass in the target parameters, and then I create a trellis LM with 99, and then I save the model here. So that's pretty much it for layer pruning. Once I have pruned it and saved it, I then push the model to hub. I do that by logging in with Hugging Face, and then I just push the model that I've saved. So I've got the repository name that I want to define the new model as on Hugging Face, and I've got my local model path, which is the modified path I've described in the script above. And I've got the original model name, which is actually only used for setting the tokenizer. And the reason why I use a slightly different model for when I say original is because I want to push the chat template. So I want to use the tokenizer from the Instruct model so that the chat template is already in place for when I come to do my final instruction fine-tuning. So you can see that is happening here because I'm loading the tokenizer from the original model name, not actually from the student model. And with that, I'm able to just push the model up to hub. And then I've got trellis SmolLM 135. I actually pushed an instruction version, but then I pushed a pruned version too. And that should be up on the hub and ready to go. If I just look here at Hugging Face, we can quickly check. And yeah, this is the raw model. And you can see the raw model is just under 200 megabytes in size, whereas the original, I think, was over, it was in the high 200s in terms of megabytes. So that's the simple layer pruning. Just very briefly to cover the more complicated width pruning. What I do here is I first do some layer pruning. So actually the first part is very similar. I start with the original parameters and then I prune the model down to target parameters 1. So here I set a first level of target parameters. Say I want to go from 135 down to 110. And then in a second step, I do the width pruning to get down to the 90. So the first step of layer pruning is actually very much the same. I use the same prune layers. And then the second step is different. It's prune hidden dimensions. And the way this works, I can just briefly go through. We start off and check the hidden size. We get that from the model config. And we check the intermediate size. And we make sure to record the ratio. So we want to keep constant the ratio between the intermediate size and the original size. We also want to know the number of heads. That's the attention heads, keys, queries, and values. And now we start the reduction. So we're going to start off and calculate a reduction ratio, which is based on the target parameters divided by the current parameters. And this is going to allow us to calculate then what our new hidden size should be. And it's important to make sure that we have divisibility. So we need to make sure that the number is going to be divisible by 32. Now, because the number of heads is always typically going to be 8 or 16, if we have a number that's divisible by 8 and then 2 and 2, it's guaranteed to be divisible by 32. So we set up the number of attention heads, the number of key value heads, and we check the models. We update in the configuration the new hidden size and the intermediate size. And yeah, you'll notice there's a square root up above in the reduction ratio, and that's because we've two values multiplied by each other that we want to give the overall reduction ratio if we're talking about a square matrix of, say, x times x. And now we need to iterate through each of the model layers, and we need to adjust the attention layers. So we're going to adjust those, fix the K, Q, V, and O, the out projection, to be reduced to this new hidden size. And then we're going to adjust the MLP layers to be adjusted to the new intermediate size and hidden size. There's an adjustment also needs to be made on the rotary dimension according to the new hidden size. So we need to do that as well and make sure that the model's rotary embedding and the frequency is appropriately resized as well. So yeah, basically it's a little bit tedious, but you need to make sure that if you resize just one dimension, everything else is going to be consistently resized so that the multiplications follow through. And now we're able to call this pruning step, which will reduce us down to target 2 number of parameters. And we can return the model, save the model, and then push it up to hub. So this is what I've done, and the model we're going to use is the layer pruned only model, which is kind of a more straightforward pruning. But as we saw in the paper, probably doing pruning of the width combined with the depth is a better approach, or possibly even hidden dimension pruning only. The intuition here is that these deeper models seem to work better for reasoning, and by pruning layers, if we do that too much, we're going to hurt the reasoning, whereas potentially there's some extra slack in the hidden dimensions that we can afford to prune away. Now, obviously, when you prune, you're removing knowledge, so the extent to which you're going to lose knowledge will depend on how many parameters you remove, and the more you remove, the more you're going to lose the base knowledge. And it's possible if there's unique knowledge being held in certain layers or certain dimensions of the matrices, you're just going to lose that outright. And just by training or distilling with 2% of data, you're never going to get back something that's contained in the rest of the data. So really what we're hoping for is that the model has kind of overrepresented things. And so there's redundancy we're taking out, which is what allows us to just distill on 2%. And empirically, that seems to be true. It seems there's a lot of redundancy in these language models. Otherwise, just doing distillation on 2% of data would not allow you to recover performance over the whole data set. We've done the student initialization, so we have a model that's pruned. It's up here on Hugging Face. And now we want to start distilling. To do that, we're going to take a look at some of the distillation scripts, namely this script here, Distillation v10, and the setup in config v10. Now, I'm going to use more GPUs here. I did do some fine tuning actually on 2% of the data, and I did it on the 99M model, and it takes about 12 hours using 8 A100s, or maybe a bit more time if you use 10 A40s, although you won't get access to those in RunPod during the day. You can get access to 8 A100s. So to deploy that, again, I'm going to go to the one-click templates and get my template for fine-tuning. And here, I'm going to select A100. It will work with A40, there's no problem there. You can just do a larger batch size, and it'll be about 2 times faster if you use an A100. Now, there's not many A40s available today, so I will just pick an A100, boost that up to 8. I've got my template here, and I'm going to deploy. Now, I've already deployed. It's this instance here. I'm just going to rename it as Distillation because I still have my instance running for layer pruning and instruction fine-tuning. And now I'm going to connect. And I'm going to connect via SSH this time. So I've copied this command here, and I'm going to head to cursor or VS Code, connect to host, add new SSH host, paste in that, add it to my config file and click connect. And I am sure I want to continue. So the VS Code server, although I'm running cursor, is going to initialize, and then it's going to allow me to clone a repository. By the way, just while that's loading, I should mention that it's probably going to be cheaper to use VastAI if you want to use A100s. If you're using A40s, RunPod is good, but VastAI, you've got a one-click template here if you want to set that up. And the prices for the A100s, let's just take a quick look. I've got, yeah, these are the A100s. You can see I can get 2 for 260 or even 2 here for 1.5. So each A100 is less than $1 per hour. So probably going to be better to use this. Now, one problem on the other hand is that you may not find it easy to rent a large amount of GPUs. So these are some trade-offs to think about. In the meantime, we are now connected via RunPod. So I'm going to clone the repository from GitHub. And I'll do that by typing in Trellis Research and looking for the advanced fine-tuning, which is this one here. So I'm going to clone that into the workspace, and that should open up. And with that open, I'll just view the terminal. And inside the terminal, I'm going to do git switch to the distillation branch. And now I can open up Distillation v10, and I can also open up my config file. So let's just take a quick look at how the distillation code works. First thing is defining a function to load and pre-process the data set. So here we're going to load a number of data sets, And the way that we've set this up, and when I say we, I mean myself and Rohan Sharma, who has helped out on a Trellis internship, and a lot of credit to him for helping pull together all of these scripts. So the data sets that we have prepared, and these are ready to go on Hugging Face. You can access them publicly. We've got Cosmopedia, and then we have a variety of chunks of the fine web data set. Now, I mentioned that SmolLM corpus, if you look at it on Hugging Face Hub, it's a mixture of a few different data sets. Let's see if we can find it here. Actually, there's SmolLM and there's very SmolLM, which is a 2% data split. And here you can see it's about 4.5 million rows. And let's see if there's any information here. There's not, but there will be on the corpus website, or rather page. So here you can see what it's comprised of. Let's see if there's a graph of the data split. I just know off the top of my head that largely this data set is fine web, and then it's got a split of Cosmopedia, maybe about 20 to 30%, and then a smaller amount of Python. So ideally you would want to take a proportion of each of those in a 2% proportion and use those for the fine tuning. What I'm going to do though is just make use of these splits, which together account for about 2% of the data, and I'll be able to quickly load these in. Now you'll notice that I've passed in this parameter streaming. This means that the full data sets are not downloaded. This is good. You could download them all, but that's, I think, a few hundred gigabytes. So you need a very large disk, which you can do. You can set that up, but it can be easier and much quicker to get started if you use streaming. Actually, it takes about 2 hours if you allow all of the data, not just to be downloaded, but mapped, because it has to be mapped into the format ready for injection into the trainer. So yeah, streaming is true, allows you to get started with a run a lot faster, and that's useful because you want to know quickly if your run is going to function properly, and then you might decide you have to shut it down and restart it with other parameters. So we're going to do unsupervised fine-tuning, and we're just going to look at the text column. So we're just going to focus on that. It's not chat templated. We're just inputting that text with the addition of an end of sequence token, which is added by the tokenizer. So our full data set is a concatenation of all of the data sets, and the evaluation data set is going to be a slice of the full data set. Now, there probably are better optimizations here on the eval data set. I think we're probably just slicing the first part of the data set. It's not mixed. It might be better to have a mixed evaluation data set, but still much better to have this eval data set than none at all. You'll notice, however, that if you take a slice of the eval data set from one of the subsplits, then it's going to show bad performance when you're on the other subsplits. So that's something just to keep in mind. Here we've got a little function for creating the training set, and it's going to be an iterable data set, and this is our mapping function here, which will allow us to tokenize it in a certain format. I'll take a quick look at that, and then we're going to remove all the columns we don't need. We only need the text column. So let's just search for tokenize function, and you can see here it's simply the student tokenizer, which is actually copied from the teacher. This student tokenizer is not copied from the instruction model because we're doing unsupervised fine-tuning. So it's going to be a very simple tokenizer that just adds an end of sequence token, and it's going to pad it out to the max length, which is 2048. If you're interested, you can check the student tokenizer here, and you can see it's been initiated from the student model. It's not being initiated from the teacher model or from an instruction model. And to be clear, both the teacher and the student in the last run I'll show here, are both the base models, not the instruct models. The reason for that is we're using a set of data that's not instruction data. And that rounds up the data set loading. It will return a train data set and an eval data set. We can take a quick look at the loading. So we're going to load the models with bfloat16. You could not do that if you're running in Collab, but you're probably not going to run this big of a training in Collab anyway on a T4. It wouldn't be recommended. We're going to use Flash Attention 2 because that's supported by A40s and A100s. Then we'll load the teacher and the student model. Make sure that the student model has got a pad token. We're just going to use the end of sequence token. And sorry, I said load the model, but I meant load the tokenizers. And down here, we load the models. Then we set the teacher into eval mode. So there's no updates of the teacher weights during the training. So we want to set it in evaluation only mode. That's forward pass only. And then we return the teacher model, student model, and the tokenizers. Now there's one more step here. Remember, in distillation, we compare the predictions of the student with the teacher. And in certain cases, the responses of the student and teacher are not the same length, in which case we need to make sure that there's going to be padding. And that's what this pad logits looks after here. Then we move on to the trainer itself. And the trainer is going to consist of allowing the teacher to do a forward pass to create logits, and then doing a forward pass on the student model and comparing those logits between the student and the teacher. So here we're just making sure that we load the teacher model and that it's on the correct device, which is CUDA or the GPUs. And then we move on to compute loss. Now, when we're doing the compute loss, we're going to use distillation loss, which is going to be a custom loss function that we've developed. And we can take a look at where that's defined. It's just defined down here, actually. And what it does is take in the logits, as I said, from teachers and students, ensuring that they're padded, and it runs forward KL-divergence. Now, additionally, if we set alpha, alpha is the blending ratio between the forward divergence and the cross-entropy. If we set it to anything less than 1, which is pure KL-divergence, then we have to add in a calculation of cross-entropy loss, which would just be between the students' logits and what the actual next token prediction is. Now I'm going to train or distill with alpha equals 1, so this is always going to default to 0, and the combined loss will just be purely the distillation loss. Now you can check out a definition for the forward KL-divergence. Let's just search for it here. And you can see, maybe we've excluded the reverse divergence because we weren't using it. So we've only got the forward divergence described, and it's, as we saw earlier on, it's going to be a log softmax of the student logits, and we calculate the teacher's log probs, which will be log softmax of the teacher logits. And with that, we're able to calculate the KL-divergence by taking in these probability distributions and then returning the KL-divergence. Now there's one more parameter here, which is the temperature. And the temperature basically allows us to kind of widen or make more narrow the distribution. Typically, a temperature of something like 1.5 to 2 is used, and that is typically going to give the best performance for measuring divergence. Basically, we're trying to take in information from a wider distribution rather than too narrow of a distribution. We're coming to the end. Here we have an evaluation loop. It's a fairly standard type of evaluation. We've added in this capability here where we can chunk up the evaluation. This can reduce your memory requirements, not necessarily essential, but we're just doing a forward pass here on the eval dataset to test what the eval loss is. Now we've got some printing of different memory stats here. We have a custom learning rate scheduler. This will run the learning rate for 90% of the run based on the settings I put in config. And then for the last 10%, it's going to do a linear anneal. This annealing is recommended because it means you can just train at constant learning rate rather than cosine, and you can easily restart at any point during that training without worrying about where you are on the cosine curve. And this annealing at the end just allows the model to settle down into any lower kind of optimum point where the loss is going to be minimized. So here now in the main part of our script, you can see we're going to define the total samples. Because we're streaming, we need to tell the trainer what the total samples are because it's only seeing batches come in. It doesn't know when it will get to the end. So we define the total samples, we define the batch size and the gradient accumulation steps. We want the product of batch size and grad accumulation steps to be roughly 32 or 64 virtual batch size. The number of GPUs is going to be counted, and we can define the number of epochs that's in the config file. The max steps is going to be determined based on the total samples divided by the batch size, divided by the gradient accumulation, divided by the number of GPUs, and divided by the number of epochs. Multiplied by the number of epochs. And said differently, this here is the virtual batch size, and the virtual batch size times number of GPUs is the total batch size when we're looking at all GPUs, because all of those results will be crushed together and used to make the backward pass update. So next, we're going to initialize some initial phase steps. This is just the amount of steps up until the annealing, so it's 90% of the steps. Define warm-up steps. We can optionally slowly ramp the learning rate at the start. I don't think it makes that much difference, but I think we warm up for about 1% of the run. Set up the run name, set up the training args. So we have the max steps, the number of epochs, the run name, logging directory. We're going to view this in tensorboard. Saving steps, we'll save every 0.1%, every 10% of the run. We'll evaluate every 10%. Warm-up steps, logging steps. The optimizer we'll use is Atom W Torch. You could use Addifactor if you want to save on VRAM. Our model's really small though, so the optimizer states, the gradients are really small, and so should the activations. Now, there does seem to be an issue in the trainer here whereby there's over allocation of memory. So we end up using up most of the memory that's on the GPU, even though technically that doesn't need to be used because we've such a small model, even for a batch size of 32. So you probably could fit a larger batch size, but either way, it wouldn't make the training any faster if we used a larger batch size. We may be able to use less GPUs, but we would have to run for longer because we're basically being limited on the total time of our run is determined by the number of computations, which is not reduced by increasing the batch size. Then we move to the distillation trainer. We pass in the model, the teacher, the training arguments, the data sets, the student tokenizer, because that's used to tokenize. Then we have the custom configuration. We can take a quick look at the custom configuration, which is actually going to come from the configuration path, which is coming from the configuration file. We'll take a look at that in a moment. Then we specify the dataset column that is going to be used, the max sequence length coming from the tokenizer, and we're also going to pack samples. So this is going to reduce the amount of padding that is added, and it will allow us to just run inference on a given sample, then a part of the next sample. It will mean that rows overflow, and it's maybe an interesting optimization to consider turning that packing off. But my guess is that it's going to reduce, well, it's not my guess, it does reduce the total rows of data that you have if you allow for packing, and so it speeds up your total training time. Now, the next thing here is gradient checkpointing. Gradient checkpointing allows you to fit more batches onto your GPU. So it's good if you only have one GPU, but it actually adds computation. So in principle, your runs will be faster if you turn off gradient checkpointing. And since we're not worried about trying to fit more batches on the GPUs, we can afford to just turn this off and gain some speed up. Here, we're preparing the accelerator. This is important if we're running on multiple GPUs. We're going to update the teacher model and datasets in the trainer. So just make sure that those are all set correctly. They should probably be set already at this point. Then we're going to configure the custom optimizer and the scheduler. And we're going to set the learning rate schedule for that trainer. And we'll add a callback so that we have some data on the memory tracker. And at this point, we're ready to print. We'll print some information around memory. We'll go through the training. We'll resume from checkpoint. If we pass, resume from checkpoint in the config. And then we're going to save the model at the end and push to hub. So that wraps up the distillation script. I'll just quickly take a look through the parameters that I've set. So this is the project name. That's for weights and biases if you use that. This is the dataset name. This is a dataset on Hugging Face Hub. Here is the number of samples. If you want to train for 2% of data, you need this to be 4.5 million rows. I did one training set just on 1 million rows, which is about 0.4% of the data. It's not enough to get the highest quality results. For eval, I've set 1,000 samples. You may want to add another 0 here, but that will slow down your eval and make your run longer as well. Then we have the training subsets. We have the models, the teacher model, the 135, the student model, which is the pruned version, the tokenizer max length, the chat template, so you can manually control the chat template. We don't use the chat template in the distillation. It's just tokenizing with an end of sequence token. But this would be relevant if you wanted to chat template and use a chat format. I'm going with a batch size of 16 and gradient accumulation of 4. So that's a virtual batch size of 64, which gives good smoothing. So it reduces the grad norm by smoothing out within a batch. We're going to use a learning rate of 1e-3. I tried 2e-3 and it's unstable. Actually, I think even lower is probably better, like 5e-4 is maybe what I would do if I was running this again. Weight decay here helps to regularize. Warm-up ratio, just a little ramp at the start. We're going to train in BrainFloat 16. Report to tensorboard. I will show you the results in tensorboard. Not going to use gradient checkpointing. And this is the name of the model once it's pushed at the end of training. Now we're going to save every 20%. I said 10%. You can vary this. And we're going to eval every 20% of steps. Just train for one epoch. And the annealing fraction is going to be the final 10%. Now for distillation, we're going to use a temperature of 2. Alpha of 1 means we're only using KL-divergence forward. We're not using cross-entropy. And yeah, these weights here are actually redundant because we've taken out of the code any options for doing reverse KL. You've also, these are different techniques you could think about as well. Probably there are a lot of ablations you could do. But if you're going to start simple, just start with KL-divergence forward. We'll use flash attention. You can set up some weights and biases parameters here, and then push to hub if necessary. Now, to get started on this script, you can take a look at the README. You'll want to pip install the requirements. So lately, as you'll see on my videos, I like using UV. So I'll do pip install UV, a Rust-based library. And then to install the requirements, I'll just run UV pip install, and I have to add system at the end if I'm not operating within a virtual environment. Usually I don't bother with a virtual environment if I'm on a run pod instance because there's already the PyTorch installed, and a virtual environment can complicate that. So then UV pip install flash attention and system. And here I would export my Hugging Face hub token. If I want to push at the end of the run, I could just type that in, copy paste, and then grab a Hugging Face token from Hugging Face. Now I'm ready to run accelerate launch. I haven't passed the token, but that's fine if I'm not going to push at the end of the run. So I'll paste this in here. Notice that I'm passing in multi-GPU and mixed precision BF16. And it should automatically detect. You can see here I've got 8 GPUs. It's just one node, and we're not using Dynamo backend. I've never looked into that. I don't quite know what that would do or if I could use it. So now you can see it's loading, downloading the model. The teacher model is about 500 megabytes. The student model is about 200 megabytes. Here you can see a printout of the student model, a printout of the teacher model here. And we're now moving on to the dataset mapping. So we're doing some mapping of the dataset. There are some deprecation warnings, and scrolling on down here, we're already up and running. So you can see this training would take about 2 hours if we run on 0.4% of the SmolLM corpus approximately. You can see the grad norm is kind of high, and the loss here is falling, which is what we want. And the learning weight is ramping because we're starting off at 5e-5, and then we're going to move up towards 1e-3. Now, to view this, you can use tensorboard. So tensorboard log dir logs. And the nice thing of doing this through cursor is that it's going to open up a port that is forwarded to my local host on my computer. So I can now check out the training here. And the training I'm running now, let's see if it's appearing just yet. I can walk you through some of the runs that I did earlier. So here, I probably should have named this something a bit smarter. I might be currently overwriting one of my previous runs. Yeah, I think we are currently probably on this purple run here. So we're on step 204, is that right? Let's lower these here. Lower this here and check. Okay, we're running on step 27. So I can refresh. We may not actually have logged any run yet. as just some representative examples of trainings, you can see here some smoother runs on the data, and here's a less smooth run. Now, when I am training, I'm looking mostly at three things. I'm looking first of all at the grad norm. So I'll go to this graph here. And if we view it on a log scale, I'm aiming for my grad norm to be below 5. Ideally, it's going to be below 1. But if I see that my grad norm is up towards 5 and it's not decreasing over time, that probably means that either I need to increase my batch size or reduce my learning rate. Now, you don't want the batch size to be too big because that will smooth too much the data and the training. So you probably don't want to go too much above 32 or 64. I mean, maybe you could go 4 times that, but don't go to like 10,000. So generally, you'll already have a large batch and just need to reduce the learning rate instead. The second thing I'm looking at is the training loss. You can see examples here of like this purple curve. You see there's a big jump. This is likely associated with moving between the different splits of the data set, but it's still probably not a great sign that I'm getting this size of jump and might be indicative that running at a lower learning rate could be worthwhile. Now, the last plot that I look at is the eval loss. So here you can see again an example of a long run where we have this continuous reduction, and that's what we want to see. Whereas in this yellow run here, we've got a nice low eval loss, but it's clearly not stable because it's jumping back up again. Potentially again related to moving through to the next part of the data set, but this is the same data set I'm using for all of the runs. So I'd be inclined to potentially lower my learning rate in this case. Now, the data set I'm currently running, I'm actually overwriting, which is not ideal. I should have given this a new name like V11. I'm currently overwriting this V10 SmolLM learning rate of 1E-3. So I'm actually overwriting this green run here. And so you're probably seeing a combination of data. Let's see if we can quickly zoom in on our grad loss here. Yeah, so here you can see the run that we're currently on in green. And this is a good sign. The grad norm is falling, which is what we like to see. We can probably take a quick look similarly here on the training loss. And again, I think my learning rate is too high. I should be at probably 5E-4. But you can see on this run here, yeah, we're steadily decreasing. And what we're hoping to avoid is this kind of pattern here in the purple where we have an instability. So far this training is going well. If I wanted to run this out, it would take about 2 hours for 0.4 of the data. So that means it's probably about 8 hours to 10 hours running on 8 A100s if I want to run through 2% of the data, which is what I would need in order to get the level of quality that at least was done in the Minitron paper, or not the Minitron paper, in the Minitron paper. Now, with the distillation done, you then want to polish off your model by doing some instruction fine-tuning. So let's take a look at that notebook. And just a quick comment that once you have done the distillation, it should push that last final model. But during the run, you may want to upload some of the results. You may want to push some of the checkpoints to hub. And the way you can do that is by pushing the results file. Now, I don't have any checkpoints saved on this run yet because I'm saving every 20% of the run. So there isn't any checkpoint created. So I'll just have to show you here that if you run the upload folder script, you're able to define the repo you want to push to. I'll often define a repo just for the checkpoints. Define the path that you want to grab logs from, which is logs. And also define the path that you want to grab the checkpoints from, which will be results. And if I run this code, it's going to create this repo and upload all of the checkpoints, including the optimizer states, so I can take off training again if my instance shuts down. And then it will also upload the logs folder so that you can view the comparisons from before. So now at this point, I have fully trained my model and I want to do instruction fine-tuning. And for that, I'm going to go back to my single A100 that I'm using for layer pruning and instruction fine-tuning, and head to that Jupyter notebook rather. And here I'm going to run these installations. These are actually all run because they're the same for layer pruning. And I'm now going to move to fine-tune the distilled model. So for fine-tuning, we're going to take in the model that I've pushed to hub. here's a model, a V10 that I ran, a base model, and it's up on Hub. And I'm now going to train on Web Instruct. Web Instruct is one of the data sets used by SmolLM for instruction fine-tuning. So if I go to Web Instruct, you can see it's a Tiger Lab data set with about 2.34 million rows. So now I'm going to decide how many rows to train on. At a minimum, you probably need 5K rows, but ideally you probably want to try and train on 50 or even 500,000 rows. You will see the eval loss is still dropping by the end of 50,000 rows, which is the longest I've done. So I'd recommend probably going for longer if you want to get the best quality. Now on a single A40, and you may want to use more GPUs if you're going to do a longer training, in which case you should run this as a Python script. But I'm just going to run it here, a batch size of 8 and gradient accumulation of 4 for an effective batch size of 32 and a learning rate of 1E-3, which should be stable here. So we're going to set up the environment, load the model and tokenizer. So here, the tokenizer we want to load is one with the right chat template, which is why I'm grabbing the instruct model of the teacher. And then the model we're loading is the pre-trained or pre-distilled or distilled model, I should say. Next, we will load and process the dataset. So this Tiger Labs dataset has got columns for question and answer. There's original and then there's question and answer. These are refined question and answers, which are better. So we're going to format those into a conversation with the user asking a question and the assistant providing an answer. Then we will format those columns of data by applying the chat template here. And we'll use the chat template from an instruct model. And here we have a function for loading and pre-processing the dataset. So we're simply loading the dataset, checking the length of rows, and we're going to select some random rows. This here is just a way of randomizing the dataset. And then we're going to format the instruction and return an array of messages. And with that, we're going to be able to map the entire dataset using this format instruction function here. So overall, this load and pre-process will return a formatted dataset. Note that it's not actually tokenizing. The tokenization will be done within the trainer. It will automatically use the chat template. And the reason it will automatically use it, I don't know if I should say automatically, is because we're going to pass this format instruction for trainer. We're going to pass that into the dataset here. Now, the SFT trainer should automatically, if you have a messages column, it should automatically use the chat template and template. But this is a more explicit approach where we're going to define the formatting function to be applied to the dataset. Moving on here, we have a custom learning rate scheduler. It's a constant learning rate, then with annealing at the end. This is actually a cosine annealing, but it really doesn't matter. You could just do linear annealing. That would be fine as well. And here in the main loop, we're going to set up the accelerator, load the model and tokenizer, define the total rows, define the training and the eval dataset, calculate the number of steps, which is the total rows divided by the batch size times gradient accumulation. That's the virtual batch size. And here multiplied then by the number of epochs, which is just 1. Note that if we use multiple GPUs, we would need to adjust the number of steps because every GPU is going to give us a multiplication factor on number of steps, or rather a dividing factor on number of steps. Then define a run name and start to set up some of the arguments. Now, broadly speaking, this is the same as in distillation, so I won't make any further comments here. We then set up the optimizer and the scheduler and get the trainer running here, passing in the model, train eval datasets, training args, tokenizer, max sequence length, the formatting function, and the optimizer with the learning rate schedule. And with that, we're ready to train. So let's see if I can get a run going here. I'll just run this cell. And at the end of the training, we'll push to hub. Turns out there is actually the datasets library that needs to be installed rather. So we will install that. And then we'll get this training done. And when the training's done, we'll be ready to push to hub. And then we'll move on to run inference on the fine-tuned model. So the model downloading is underway. We're just going to download the dataset. And while we're doing this, I'm going to SSH into my notebook just so I can see tensorboard. So I'm actually going to copy that SSH command, head to cursor, and I'm actually going to go to open up a new host connection like this, add it to my configuration file, and then connect. And I'm going to connect into the same instance that's running my Jupyter Notebook. So we should be able to see those files now momentarily. So I'll open up a folder here, which is going to be workspace. And you can see here it's got my notebooks. And shortly, once the run starts, it should also have my logs. So here in the fine-tuning notebook, you can see we have just started training. All of the data is downloaded. And I'll open up a terminal now. You can see logs SFT is there. And I can run tensorboard and logdir and then logs. So now we have tensorboard popping up for the supervised fine-tuning. And yeah, because we are still early on, tensorboard has not loaded any data yet. So over time, we will see this version of tensorboard get updated. In the meantime, what I'm going to do is I'll show you some of the logs from a run I have served earlier, just by running tensorboard in the repo I've cloned. And I'll do that by running logdir, and then I want logs SFT. And I'm realizing now why the previous logs weren't showing as well. It's because I didn't type in the right folder name. So here we'll have a copy of the logs I ran previously. And if I want a copy of the logs that I'm running now, I need to do logdir, and not logs. I need to do logs-sft. And this should show us the run that we're currently on. So yes, here is the supervised fine-tuning. And you can see we have a training loss. And yeah, we're just picking up data points, so there's not a ton of information available just yet. But I did gather some supervised fine-tuning data from earlier, which we can take a quick look at now. And you can see here, if you just run for a total of like 200 steps, the training loss is still falling fairly rapidly, even at the point of running 2,000 steps, which is the equivalent of 50,000 rows of data, I think. There's still a reduction here happening in the training loss and probably room for improvement. We can check the gradient norm, and the gradient norms look good. They're decreasing throughout these runs. And we can also check the eval loss, and you can see even the eval loss is falling when I'm doing fine-tuning out to 50,000 rows. So the supervised fine-tuning has a pretty significant effect on the performance, and we'll see that now when we run some inference. So I'll just keep allowing that to run. Everything looks fine on supervised fine-tuning. And in the meantime, we will do some inference of the models. So there are two sets of code here for inference. You can inference the original distilled model, or you can inference the fine-tuned distilled model. So let's start off by looking at the original distilled model. We've got a function to load the model, set up the device, and then we have some completion-based prompting. So completion-based prompting is where you just give it kind of some words that it could naturally follow on with, like a classic is 1, 2, 3. And the first model I want to show you is one of the original models. So let's take a look here at the SmolLM base model, which was created by Hugging Face. And let's take a look at the kind of performance we get from that. And before we do that, I'm actually going to have to stop the training, which I'm just going to do now. So the training here has been stopped, I believe. And now I can run inference on the original SmolLM model. So here you can see the capital Francis Paris, the capital Francis Paris, capital Francis Paris. So basically it's getting the answer right, but because it's a base model, it's not able to, it's got a lot of repetition within the model. And we can compare that now to the Instruct model. So even if we do a completion-based approach, you can see the capital Francis Paris, the largest city in France, and cultural and economic hub of the country. And it goes on to give history. So yeah, there's a really big difference between Instruct and base model, and that shows the massive impact of supervised fine-tuning. So definitely don't neglect supervised fine-tuning if you want a good distilled model. Now, the next thing I want to show you is what it looks like if you just inference a pruned model. So we can prune here. Let's take a look at this layer pruned model, which is the one that I showed in the demo today, and see what kind of results we get here. So yeah, this is what you get when you prune a model. If you take out layers, you start to get answers that are fairly rubbishy. Now, interestingly, you can look at different ways of pruning and see how they perform. So for example, here's one I prepared. It's naive layer width pruning. And if we take a look at this model, you can see there are still words actually that are intact. So somehow the model response is a bit more intact if you do a combination of layer and width than if you just do the layer type pruning. Now, I wouldn't say necessarily this is an indicator of the best way of pruning. It just shows you that without any extra adjustment, this is what the pruning does to the model. And last of all, we can take a look at a distilled model. So for example, I have this Trellis 99 V10 base, and let's have a look at how this performs. So the capital of France is the largest and most important capital of the world. So you can see that the distillation now gets it to respond coherently. It's not picking out Paris as the right answer, and it is doing repetition, which we expect from a base model, but it's certainly improved quite a bit by doing the distillation. So like the wheels on the bus go 100 miles, and the bus is 100 miles. They're proper words, but the answers are not entirely coherent. So more or better distillation is required here, and then clearly we need instruction fine-tuning on top of this. So let's now look at instruction models. So we have some functions now that are set up with chat templating to answer clean questions and then give a response. So I have 5 questions set up here, and we have a few options. So we can look at option 0, which is just the instruct model, the parent model, or the teacher model. And then let's see what other ones might we want to look at. We can take a look at this instruct model that I've trained, option 5, which is a distilled and then instruction tuned model. So let's take a look at option 0, and let's take a look at option 5. So here we are with Hugging Face's work, and it's quite a beautiful model. What is the capital of France? It's Paris. It's the largest city in France, second largest in the world. It's located in the north central region of France on the Seine River. Yeah, so this is pretty beautiful. Gravity, it's pretty great. Derivative of a function, universe, how to kill, the age-old question of killing. Yeah, I mean, that's a pretty great answer. It's a pretty well-aligned model here. So yeah, I think this is really impressive what Hugging Face have done on making these small models, and it's not trivial to distill. But let's take a look at effort 5 here. So we put in number 5. It's downloading now. You can see it's a smaller model, just under 200 megabytes in size. Let's see how this performs. So here, what's the capital of France? The capital of France is the capital of France, which is located in the capital city of France. So not entirely coherent. Explain the concept of gravity. Gravity is a force that causes an object to move towards the observer. Yeah, I mean, it's in the right domain, but it's not describing it properly. The same with the derivative question. What is the universe? And then how to kill is given an example with leaves. So broadly speaking, we have answers here that are getting to be more coherent. Yeah, like this is kind of on track. So you can see that distilling has brought us a massive way from just the pruned model, which is completely incoherent, and the instruction fine-tuning has brought us answers that are now no longer including too much repetition, although you can see a little bit of repetition here. So hopefully this gives you a quick sense of what it means to prune models in terms of quality, what the distillation does, and then what the instruction fine-tuning does on top of that. And that brings us full circle on the distillation process. So now we're ready for a few final tips. I don't know about advanced tips, but maybe let's just put in final tips. First off, on pruning, probably layer pruning is the most straightforward, although hidden dimension pruning or width pruning probably gives a bit better performance, especially if you optimized it based on looking at losses of the activations, which, by the way, I didn't go into detail on here. For the learning rate, just keep looking at the grad norm. Make sure it's dropping. Ideally, you want to get it towards less than 1. Think about having a large effective batch size of 32 or 64 controlled via number of GPUs, gradient accumulation, and batch size. Probably pruning smaller models is more difficult. So while what I did was good as a demo because it's a small model and doesn't take too many GPUs, it's bad because it requires me to basically cut out of a model that's already small and probably is relying on a lot of the pieces. So there may not be that much redundancy in a small model, maybe there's more likely to be redundancy in a bigger model, and that's potentially why in the, say, Minitron paper, they're able to prune quite effectively from 8 billion down to 4 billion parameters, or from 12 down to 8 in the case of Mistral Nemo Minitron. And yeah, last of all, instruction fine-tuning is very important. And probably I would extend that to say instruction fine-tuning and preference optimization. That's going to have a meaningful impact on the quality of answers. And I think the quality of the SmolLM models is probably testament not just to the good pre-training that Hugging Face did, but also to the phase of instruction fine-tuning as well. And that's it for this overview of distillation. You can get access to the scripts over on trellis.com. I'll also put all of the links to the papers and the relative repos and datasets right below in the description. In the meantime, let me know if you have any questions in the comments below. Cheers, folks.